Echinochimaera was a very strange fish coming from the Bear Gulch Limestone of Montana, and this is one of the premier Lagerstätte for finding fish from this time period during the Carboniferous about 320 million years ago. There hasn't been as much work on how all these fossils formed, but there are so many we can get a really good understanding of this ecosystem, and it's pretty different from modern-day oceans. And that's in part because when you're thinking of fish in modern-day oceans, you're probably thinking of something like a great white shark, which obviously sharks have a great hold on the human psyche. Alternatively, you're thinking of what makes up almost 50% of all vertebrates today, not just fish, vertebrates, and those are the Echinochimaera, the ray-finned fish. However, fossils from this site show that it wasn't quite the same. There were more of other kinds of fish, like the Echinochimaera, which are the lobe-finned fish. Think of things like coelacanths and also eventually lungfish and tetrapods like us. In the Bear Gulch Limestone, there's one agnathan, meaning it would have been a lamprey. There's also an acanthodine, meaning it would have been a stem shark. Essentially, on the lineage that led to sharks, it was an early branch of that lineage. And on that subject of sharks, the sharks are the elasmobranchs, and next to the elasmobranchs as their sister group are the holocephalians, and there will be a lot about both of these groups later. However, importantly, there were a lot of them in the Bear Gulch Limestone, more than we would expect in a modern-day ecosystem. And importantly, 63 of them weren't sharks, they weren't elasmobranchs. Additionally, there were some sharks that were in there, over 20 different species being found. Finally, there were 6 species of coelacanth and 49 Echinochimaera. However, by just sheer numbers, the coelacanths are the most commonly found. Not necessarily there were more species of them, just those were the most common animals in the habitat. This is really strange when you think about modern-day coelacanths, and that's largely because they mostly live in relatively deep water and aren't particularly numerous. So having so many of them in one habitat really helps to show just how different the oceans were during the Carboniferous. The sharks from the formation are also pretty strange, some of them being weird eel-like forms like Lystracanthus and Thrinacotis. And this kind of odd ocean is where Echinochimaera would have lived. And there's enough of them to be able to say pretty confidently it would have been a chondrichthyan. That's in part because the fossils don't actually seem to preserve the same way that bone does in other fish, and instead more like cartilage in known chondrichthyans. Additionally, there's enough of a sample size that we can see claspers in some of them. Claspers being mating organs for the males and helps them to be able to actually reproduce. There's also 2 species of Echinochimaera that have been found. Echinochimaera melanin and Echinochimaera snyderi. And there are differences in the tooth plates to be able to show that, yeah, these are definitely different species and would have been feeding at least slightly differently despite being very visually similar. So even within just this one genus at Bear Gulch, there's still pretty good diversity, and it helps to show that they were doing different things and adapting to different circumstances in their environment. But also importantly, based even just on their name, there is a really good clue as to what they were. And that's because they were closely related to the Chimeras, which are the only living members of the holocephalians around today. When people use the term sharks today, they often use it to mean all chondrichthyans, and that's not accurate because, again, the holocephalians are still around, they just mostly live in the deep sea where people don't really see them. They're also very bizarre looking, so it's not necessarily the first thing that jumps to mind when someone shouts, shark. Because of this large assumption that all chondrichthyans are sharks, there's been a long-standing history of going, oh, well, sharks are unchanged for hundreds of millions of years, without looking at the broader diversity that they had, and especially when you're considering sharks in the Paleozoic, that is, before the Permian-Triassic extinction, where the oceans radically changed and became much more like modern oceans. A lot of those sharks aren't actually sharks, but are holocephalians. But Echinochimaera isn't basically just a modern-day chimeran that was living around 324 million years ago. Instead, it was its own animal adapted to its environment. And it was a different environment because Bear Gulch shows a lot of evidence of being at least relatively shallow, as opposed to in the modern day where chimerans live very far down below the ocean surface, hundreds if not thousands of feet deep. This means, well, if you wanted to be able to use a hook and line in order to catch a modern day chimera, you'd need the right bait of something that's very hard, and then be able to also get a boat out far enough that they could live there, and then also drop that bait down and haul it all the way up to the surface, which that's a pretty large prospect. You could potentially catch something like a Echinochimaera just from casting from the shore, if you were casting from the shore 320 some odd million years ago. One of the adaptations for this very unique diet of eating very hard-shelled mollusks and crustaceans that we see in modern-day chimeras is that their tooth plates don't actually fall out and get replaced the way we see in sharks, where sharks are constantly replacing their teeth. Chimeras just keep their teeth all the time. That means they have a much weaker fossil record overall as opposed to sharks. And again, that's just because there's not constantly teeth defined. That means we just have these very little glimpses into the evolution of modern day chimeras. And it seems like Echinochimaera was pretty close to that lineage that would lead to the modern day chimeras, in part because it seems like it had similar teeth. Instead of losing teeth and growing in new ones, the same teeth just grew throughout its life. And I say that because we don't really find isolated tooth batteries throughout the Bear Gulch Limestone. If they were living there, they'd be losing teeth in those same sediments, and we would expect to find those fossilized without the rest of the body. And that just doesn't seem to happen. That said, because they were in shallower seas, there were other things happening with their biology. Notably, the Bear Gulch Limestone is overwhelmingly dominated, at least in Echinochimaera, by male juveniles, meaning there was potentially some sexual selection going on in this species, where there's a lot more males produced, and then only a few of those are chosen as mates by the females during the breeding season. This also could mean that the young females actually moved more offshore when they were first born, potentially just targeting different food sources or living in a more secluded area as opposed to the shallower seas where there might be more predation. This sort of trait of being more offshore then may have also just slowly been picked up by the males through evolutionary pressure, where, yeah, sure, it's great to be in these shallow waters where they can eat more, but also maybe if they just move offshore, they're going to be safer overall. And then potentially that kind of behavioral shift could have led to why chimerids are actually living in the deep sea today as opposed to in shallow waters. But Echinochimaera is only part of one lineage of the holocephalians. There's also other things like the eugenodonts, which are these weird whortle-toothed shark-like animals. And by shark-like, I mean they would have been swimming in the open ocean and probably been pretty shark-shaped. But again, not sharks, in part because of how their skull was actually built. The palatoquadrate is this really key feature in modern day sharks because it can kind of actually detach from the rest of the skull. The most extreme example of it is going to be in the goblin shark. The reason it can reach its jaw so far forward is because the entire palatoquadrate bone, not a bone because it's cartilage in sharks, but that entire structure detaches from the skull and can move forward. However, in things like the eugenodonts, such as holocephalians, that's actually still fixed to the upper part of the skull. It can't move independently, but it's still not entirely fused together. However, when we do get into things like Echinochimaera and later modern-day chimerids, it is entirely fused as one piece. In fact, the palatoquadrate, the part of the jaw, actually becomes part of the brain case in them. So you can see how there's this really different kind of jaw morphology that helps us to understand what these different groups actually were related to. Holocephalians, along with Echinochimaera, really helps to highlight how different some of these holocephalians could have been in the fossil record. And when you're looking at things like Holocephalians, it could reach large sizes, up to 20 feet or a little over 6 meters. And as for its odd jaw whorl, it seems like it would have been very good at being able to bite onto the more fleshy part of things like ammonites, and then use that whorl to pull them back and essentially shuck them out of the shell. Additionally, when it's reaching that large of a size, it's still going to be able to slice larger things like fish pretty easily. And then there's the Iniopterygians, for which it seems like there's a couple of different ideas about how they might have lived. And overall, the currently winning one is being more pelagic and using their very high up fins to actually escape from predators the way we see in modern day flying fish. But again, chondrichthyan and a holocephalian at that. This thing is closer to chimeras that live very deep, but they may have been living near the ocean surface and escaping from predators by flying around, or at least gliding around. I personally still think there needs to be a lot more work done on this group, in part because some of them, like Ranierichthyes, aren't necessarily as streamlined as you might expect for the group. Additionally, you have some of them that seem to be very well adapted for high-powered suction feeding, which could mean one of two things. One, they were actually swimming through the water and being able to use this suction feeding in order to filter feed. Alternatively, when you're looking at some of them, they still have at least somewhat notable teeth, meaning instead maybe they were using their fins more like what you see in modern day frogfish, where they can move around reef systems and then use rapid suction feeding to pull in prey. Ranierichthyes actually came from the Mason Creek deposits, which is closer to shore, so that actually might have some good standing, and who knows, maybe some individuals in this group were doing very different things. Again, there needs to be a lot more work done on the Iniopterygians, but again, just highlighting how different the animals closer to chimeras were as opposed to the animals closer to sharks, which for most of their history, sharks stayed pretty similar. And oftentimes you actually find sharks, or at least early sharks, more in freshwater ecosystems, and otherwise just kind of hanging around shorelines and reefs, but not necessarily being as dominant as we expect today. That said, the Permian-Triassic extinction, which I alluded to earlier, was devastating in the ocean. Up to 95% of animals in the ocean died off, and that includes a lot of the holocephalians. And potentially that's the reason the Chimeras are the only ones around today. They were the ones that were most adapted to eating what scraps were left over. And from that, they were able to re-diversify a bit during the Mesozoic, but sharks did so much more, which is why we now have these shark-dominated ecosystems in many parts of the world, whereas chimeras just live way down in the depths. So overall, what is a Echinochimaera? It's a weird chimerid relative, and potentially even really close to that lineage, and potentially even a missing link to how the chimerids began to start colonizing the deep ocean. However, also very importantly, it's just one stop on that lineage, and it's a very rare stop where we have fossils of the entire body. Cartilaginous fish, including sharks and holocephalians, don't really fossilize that well, which means we just have these little glimpses into their evolution. However, with sharks, we actually have a good number of their teeth, so we can say certain things about them. And what it seems like is before the Permian-Triassic extinction, they were much more common in freshwater environments than they are today. And that includes with things like xenocanthus. However, there were still some out in the oceans, but none of those out in the ocean match the diversity and broad range of lifestyles that we see in the holocephalians. Which is kind of tragic now that you look at the holocephalians and go, oh, they're just bottom dwellers that kind of eat random mollusks and crustaceans. Not really as exciting as what you think about when you're thinking of things like Helicoprion, or even the really weird Iniopterygians. But Echinochimaera is really important for linking those together, and helping us to understand the broad diversity of what's now one of the rarest groups of animals on the Earth, in part because they live so far down, and in part because so much overfishing of the oceans is potentially just destroying lots of their habitat, and we really should work better at trying to protect that. Hey everyone, thanks for watching, and real quick, things like Echinochimaera would have lived alongside the Eurypterids, which can be seen on this shirt, and this is just a prototype. However, we are beginning to actually set up all of the systems in place to be able to actually start selling shirts like this and a few others. Now, I do want to keep in mind that this is our first time launching this kind of website. We don't know how much demand there's going to be, so some of the ordering might be going slow. However, it only takes a few days for us to just get all those materials in, so it shouldn't take too long for us to be able to ship them if they are out of stock at a moment. So just be aware, we're going to be working with you guys on this, and hopefully you guys are going to be very interested in what we have to sell. Additionally, for our patrons, hey, guess what? You guys are probably going to get a discount on this. We're going to look into setting that up, and we really appreciate it. So look out for discounts through the Patreon.